Okay. Okay, so to start with, are there any questions? Yes.
I'm having a little bit of trouble with the simulation. Trying to figure out how to get to deal with the extra queue.
We're talking about homework 5. Okay, so in homework 5 is a relatively simple change from homework 3. And just as when you went from homework 3 to homework 4, what you do is you made a change in homework 1. And now you have to make a similar change. So in homework 3, when you went from the case where you had essentially an infinite number of sources to the case when there was a finite number of sources, what you did was you had to define an array that took into account the state of the sources. Well, now you define an array that takes into account the state of the waiting positions. You don't have to move customers around in the waiting positions. All you have to know is whether or not whenever a customer arrives, all waiting positions are occupied. And if all waiting positions are occupied, then the incoming customer is lost. If not, then the new customer would occupy one of the waiting positions. And he would hold it for a length of time, which is his waiting time. And so you would use that information to update the state of the waiting position. So what you do with the waiting positions in this homework is analogous to what you did with the sources in the previous homework. So with that hint, this should be easy. So that answers part of your question, right? Then you had some other question.
Going over the breakdown equations for the single source system, I think I actually got it now.
Okay, so the question is, give us a little review of homework 5. Okay, so here's homework 5. So you have MM1. Now, for this you have to calculate some stuff. So let's see. You have this table. And you're going to do this for 2 cases. Case 1, you're going to have 0.8 Erlangs. And case 2, you're going to have 1.2 Erlangs. In some sense, it doesn't make any difference, except, of course, numerically. But when n is equal to infinity, it does make a difference, because in that case, you have to worry about convergence. But for any finite number of waiting positions, you don't have to worry about convergence. So we're talking about MM1. I didn't really finish this. MM1n. What that means is that, at least in our notation, we have a server, and then we have some waiting positions, and the number of waiting positions is n. And if a customer arrives and he finds all waiting positions occupied, then he's a lost customer, and they arrive according to a Poisson process with rate lambda, and we'll assume that we have exponential service times with rate mu. Of course, since we know that A is equal to lambda over mu, we can take mu to be 1. That's a convention. And then the offered load and the arrival rate would be numerically equal to the same thing. Okay, but it doesn't make any difference how you do it as long as ultimately you get the right answers. So we're going to look at this for various values of n. 0, 1, 2, and so forth, up to 32, and then infinity. Now, the case in which n is finite, you've already done this, or this has already been done in exercise number 5 in chapter 1. So exercise 5 in chapter 1, you already looked at this And in fact, in that case, what you looked at was M, M, S, N. So if you go back to what was done there, and the solutions are in the solution manual, then if you just set S equal 1, then you're going to have some of the answers. Now here it asks you to calculate certain things. It asks you to calculate rho, pi sub n plus 1, and W of n. And it asks, of course, as usual, to do theory and simulation. Theory, simulation. And theory, simulation. And I don't think I gave a due date for this problem, so let me make it a week from today. Now, in parallel, you should be thinking that the next exercise is going to change the M to D. So, in fact, you can look at both of these as being a special case of MG1N. But for the case of MM1N, we can use the rate up equals down argument, and so that makes everything relatively simple. So the strategy here is to look at exercise, homework 5. All right, so this is homework 5. And this one with the D is homework 6. So for homework 5, the theory should be relatively simple, and the simulation is sort of simple too, but you have to figure that out. When you get the theory and the simulation to agree, then you can be fairly certain that your simulation is correct. So that means that when you go to homework 6, the simulation is exactly the same except for the one instruction that generates the service times. So you know your simulation is correct, and all of the emphasis, all the difficulty in homework 6 is on the theory. So you don't know how to do that theory yet, so I want to start talking about that. Now, this is the utilization, so you know how to do this. This represents the probability that an arriving customer finds the system in state n plus 1. Now, since we have one server and n waiting positions, this is the probability that an arrival finds all the waiting positions occupied, the buffer full, and is therefore lost. So this is the lost probability. And because we have Poisson input, the pi's and the p's are the same, and the p's are obtained by writing rate up equals rate down. This represents the average waiting time for the system with n waiting positions in the case, case of n waiting positions. The point here is that I wanted to find the average waiting time to be applied only for those customers who were actually carried. Because if a customer is lost, there are two possibilities you could think of. One is to say that his waiting time is infinite because he never gets carried. But if you add that in, then the average waiting time for everybody would be infinite, so you wouldn't get any information out of that. On the other hand, if you took the waiting time for the lost customers to be 0, then that would weight the waiting times to indicate that you're giving better service than you are. Because it's true maybe that the lost customers didn't wait, but they didn't get served either, so you wouldn't want to assign to them a waiting time of 0, which indicates that they got served immediately. So what you need here is the conditional waiting time, given that you're talking about customers who ultimately get served. So you have to figure out how to do this. Not that this is all that hard, but this is something that you haven't done before. So right now, my strategy is to give these problems, and in each problem give you a little bit less information in a sense, so that ultimately you can do them on your own. So in homework 1, I told you everything. In homework 2, I told you a little less. Homework 3, a little less, and so on. So now I want you to figure out how to do this yourself. Now for this particular case, that is for MM1N, you could actually derive a formula for this. And since there's a simple formula, that means that formula could be found someplace. So you could find it on the internet. You could find it in the book someplace maybe. I have it written down somewhere. So it's an easy formula. So when you get it, it gives you a good check to see whether or not what you're doing is right. However, I'm not recommending you do that. Because for one thing, using that formula is going to be no help in homework 6, because in homework 6, the theory is much different. The methods for calculating are much different, and there are no closed form formulas. So it's probably better to do homework 5 using the same strategy that you're going to use for homework 6. So you don't have to make a major change. However, if you do find this formula, that's fine, you can use it, but that shouldn't be the end. So if you have some formula that allows you to calculate these things in theory, then say what it is, say where you got it. If you can derive it yourself, that's great. If you can't, well, then you're just looking something up in a book. So that's better than nothing if you have the right formula, but not as good as knowing what you're doing. But whatever it is, just tell me what it is so I can see the line of reasoning that led to it. In the simulation, of course, all you do is every time a customer waits, every time a customer arrives who is not lost, you would simply calculate his waiting time, and then you add up all the waiting times, divide by the total number of customers who are not lost. That is the total number of customers who are carried, and that will give you the average waiting time for the carried customers. Now, for this case and this case, these are checks in a sense, because in this case, the theory is simple because this is an Erlang B model with one server. So therefore, I know that rho is equal to the carried load divided by the number of servers. The number of servers is 1. So the carried load carried load is equal to the average number of servers, average number of busy servers. That's the carried load by definition. Divided. So the utilization is the carried load divided by the number of servers. The carried load is the average number of busy servers. So you have formulas for that in the case in which n is equal to 0. That's just the Erlang B model. And in fact, I can write down immediately that in the Erlang B, for one server, an offered load of A Erlangs is A over 1 plus A. And that, is, of course, is the probability of being in state 1, and it's the probability of finding state 1. So this value right here would be the Erlang B value. This value is the carried load for Erlang B divided by 1, which is the carried load. And this value intuitively is 0, because in an Erlang B case, there are no waiting positions. So everybody who gets carried must enter the server immediately, in which case his waiting time is 0. Of course, that'll be a good check on your simulation to see if it works. So this one is fairly easy. Now, this is just the Erlang C model. So this is the Erlang C model with one server. And if you remember that the Erlang C value, C of 1A, was equal to A if A is less than 1. So in the case in which we have an offered load of 0.8 Erlangs and the offered load of 1.2 Erlangs, case 2, then the case between 0 and 32, that is for a finite number of n, they're all the same except for different numbers. But when n is equal to infinity, you have to realize that case number 1, your answers are given by the Erlang C values, Erlang C probabilities, and case number 2, you don't have convergence. So in fact, the fraction of customers who, what would happen is in the infinite case, you would have the Erlang C value could be viewed as being 1. So remember when in homework 3 that you looked at the case in which the offered load was greater than the number of servers. So this is somewhat similar. Not exactly the same thing, because previously I didn't ask for this value right here. In any event, this case and this case are calculated differently, or they can be calculated differently, separately. Now, when you run the simulation, of course, you can't run it for n is equal to infinity. You can make n very large, but that's not what I'm looking for here. What I want you to do in the simulation is take the values you would get if you ran your simulation for homework 3, in which the number of waiting positions is assumed to be infinite. That's implied in the simulation, and use those values. Okay, so this then, I think, with that should be straightforward. Okay, so how do you calculate these probabilities? Well, what you want to do is you want to write rate up equals rate down. So those equations look like this. The rate up from state J is lambda Pj, and the rate down from state J plus 1 is, well, here's the Pj plus 1. I have to multiply that by mu sub J plus 1. That's the aggregate service completion rate when I'm in state J plus 1. But if you recognize when I have one server, that means that the aggregate service completion rate is always equal to 1 over tau, because no matter how long the queue is, there's still only one customer being served. So mu sub j, I'll write it this way, mu sub k is equal to mu, which we could take as being 1, mu or 1 over tau. So you write these equations. Now, you could solve them by recursively, mathematically, getting each p in terms of the previous p, and then getting everything in terms of p0, normalizing. And in fact, that's what's done in this example 5 in chapter 1. But another way to do it, if you're interested in the numerical values rather than improving theorems, another way to do it is to do it by simply solving these equations numerically. And I think I mentioned that before, and before, though, it really wasn't necessary, but now it's going to be much better to do it this way because of what's going to come in homework number 6. So the idea here is that I can find each p in terms of the previous one. So what I do is I set p0 equal to some arbitrary value like 1, and that gives me p1. And then I find p2 in terms of p1 and p3 in terms of p2 and so forth. So then I have all of the p's, but they're going to be the wrong numbers because they're not going to add up to 1. So no matter what I choose for p0, as long as it's some positive number, that means that the probabilities are all going to be correct relative to each other, but they're not going to be absolutely correct because they won't sum to 1 unless you just happen to guess the right value for p0. So what you do is you calculate the p's numerically by calculating each p from the previous p, and then you store them as you calculate them, and then at the end you divide each one of those things, including the initial value of 1, by the sum of all of them, and that normalizes them, and so then they will add up to 1. Okay, then you know the probabilities, and now you can calculate things like, well, you'll know pi sub n plus 1, and you can calculate this because this is going to involve some kind of expected value, which involves those probabilities, and so you can calculate this from those numerical values. Once you got that, of course, it's the same thing for every value of n. You just run the same program for a bigger value of n. Okay, now, what happens in homework 6? In homework 6, the picture looks the same, but now the service times are not assumed to be exponential. So what's the problem? In other words, what I'm asking is, why can't I write rate up equals rate down for the case in which the service times are not exponential? What's the problem? Problem is that these equations assume that there's no memory, in the sense that what this says is that the rate at which I go up and the rate at which I go down depend only on the state of the system. State is defined as the number of customers present and has nothing to do with the prior history that got me there. So it has nothing, it doesn't reflect the lengths of times involved. It only reflects the total number that are present. So if I were to draw a picture, for example, looks like this. So a customer arrives, and let's say he arrives and the server is idle, so he makes the server busy, and he holds the server for a certain length of time. That's his service time. Then another customer arrives, and he makes the server busy later. That's his service time. And another one arrives, and that's his service time, and so forth. Except for the first customer in this busy period, every other customer arrives during a service time. Now, if the service times are exponential, that means that from the viewpoint of the arriving customer, the service time that he interrupts has a remainder that's exactly the same as if it was starting from the beginning. So therefore, you don't need to know how long the customer who is interrupted was in service. That's what makes it easy. But if the service times are not exponential, that means that the interrupted service time, the time remaining, is going to depend on the amount of time that was expired. So for example, in the most extreme case, extreme in a certain sense, if these intervals, service times, are exponential, then the time from here to here, there is no memory whatever. If these intervals are constant, as in MD1, then the time from here to here is completely known if you know how much time has elapsed. In other words, in the exponential case, the elapsed time gives me no information about the future. And in the constant case, the elapsed time gives me exact, precise information about the future. And every other case is intermediate. Furthermore, as you might remember from homework 2, if the service times are not exponential, then the distribution, if the service times are not constant, then the distribution of the interrupted interval is different from the distribution of an arbitrary interval. And that has to be taken into account too. And so we'll worry about that when we look at MG1. But for MD1, at least we don't have that problem. In any event, the point here is that if we don't have exponential service times, then you don't have the conditions that are sufficient to be able to write rate up equals rate down without taking into account any of the past history. So I have to show you later how to write the equations for the case in which the service times are not exponential. And then when you write those equations, you can't solve them. You can't solve them mathematically in general, but you can solve them numerically because you'll have an array of equations and you could solve each one numerically in terms of the previous one. And so by that argument, you can get all of the probabilities and then you can calculate all the stuff that's in here, at least if you know how to do that, which I will show you. Okay? So that's the big picture here. So any questions about this? So let's make this due a week from today. And then let's make the next homework due a week after that, although maybe we'll need more time. That depends on how it goes. So this homework should be not hard. Okay, so have I told you everything I need to tell you about this? But you still have time to ask questions, right? You can ask questions on next week. And I guess if you don't have it done and you still have questions on the time it's due, as usual, although I don't recommend it, I'm not asking you to do this, I will accept late homeworks because for me the important thing is that you understand it and you get it right, not that you get it in on time. But that's not supposed to be a license to not do it. Right? You're supposed to do it and get it in on time if possible. Okay. Basically, the later it is, the less forgiving I'll be in giving grades on it. But I can't say something like, well, you lose a point for every day or anything like that. That's silly. Okay, so now I'd like to look at the MG1Q. And, well, let's see, one more thing. Let's go back over to here. In this case, I can get the answer here. You have a formula for this. The reason here is that when n goes to infinity, then if a is less than s, if a is less than 1, as is true in case 1, not in case 2, then what that means is that everybody who arrives gets served. And therefore, as n goes to infinity, this is just going to be the Erlang C model because you don't have to worry about the condition that what happens to the customers who are denied service. That doesn't happen. So you have a formula for this in that case. Okay. Now, if you work that formula out, you're going to get some answer. And if I remember, I'm not sure what the answer is, but it's going to be different than in the case in which the service times are constant. And in fact, as we'll see shortly, there's going to be a 2-to-1 difference. So one of the things I'm trying to do is show what the effect of the service times are. And what we've done in the course so far is, in every case where we really understood what was going on, where we had some theory, either the service times were assumed to be exponential, or it didn't matter whether they were exponential or not because we had insensitivity. But now it matters, and in addition, we're going to have formulas for it, so you can see explicitly what the effect is of constant service times versus exponential service times for the same amount of traffic. And in some cases, it'll make a difference, and in some cases, it won't make a difference. For example, in the MD1 case, over here, the utilization will be equal to the offered load. And that'll be true whether I have exponential service times or constant service times or anything else, because everybody who arrives gets served. So from Little's theorem, it'll turn out that the server is just as busy in case 2 in homework 6 as it is in homework 5. But the fraction of customers who overflow the buffers is going to be different, and the average waiting time is going to be different. And what will happen in those homeworks is when you run the simulation and do the theory and compare the corresponding results for homework 5 and homework 6, you'll see what the effect is of having the less variable service time. All right, so I would like to discuss now, that is, change gears for a moment and discuss MG1 from the viewpoint of the stochastic models course. So if you took the stochastic models course, you might recall that there was a homework 6 entitled MG1, and it had a simulation using a method, something called Linley's equation, and then I gave you some formulas. So I want to go over that. So if you took the stochastic models course, you should look back at your homeworks and review that one. And if you didn't take the stochastic models course, you should download that homework and study it. And it's easy to do. So you could run the homework, because remember, this is, well, I'll explain as I discuss this what the strategy is in terms of the stochastic models course, which presumes that you don't know any queuing theory and don't want to know any queuing theory. And even though you've just taken a course in probability, you don't know any probability theory either. And maybe you still don't even want to know any probability theory. Okay, so I'm going to pass this around. There's 2 pages here for each, one on the top and one on the bottom for homework 6. So what it says is, all right, let me start with where we are. It's homework 6 in the stochastic models course. So this is for STA 4821, homework 6. So you go to the website, you download homework 6. And the title is the MG1Q. MG1Q. So the MG1Q, this is now the case in which we have an infinite number of waiting positions, and it includes the exponential case and the constant case as special cases. And in the case of exponential, it's just the Erlang delay model. And in the constant case with MD1, it's going to be the case that we're going to do in homework 6 in this course for the case of an infinite number of waiting positions. So when the number of waiting positions is infinite, we can get some formulas. But when the number of waiting positions is finite, then you have to actually solve the equations numerically. So it says the following basic code simulates a single server queue with FIFO service. It generates the inter-arrival times and the service times for 100,000 customers and produces estimates of the server utilization, the fraction of customers who must wait in the queue, and the average waiting time. And then I give the code. And then I say adapt the program and run it using the language of your choice. Of course, BASIC is the easiest, for 3 different service time distributions. And those are exponential, constant, or uniform, and they're all the case where the average service time is 1/2. So they're comparable. They're all going to produce the same load. And it says assume that the inter-arrival times are exponentially distributed with a mean value of 0.625. That is, we have Poisson arrivals with lambda is equal to 1.6. Then it says fill in a table and stuff like that. So there's 2 things I want to do here. First, I want to go over the theory. And then I want to look at the simulation. So the theory says, the way this homework is stated, it says theory for the MG1Q, and then it gives some formulas. Now, from our viewpoint, we're going to derive these formulas. But from that viewpoint, I just wanted to give them because I wanted to make a couple of points here. One is that this is a very complicated problem. Nevertheless, I can come up with closed form formulas in some cases. And so this introduces queuing theory. From a probability point of view, for students taking a course like the Stochastic Models course, this is on the boundary between a toy homework problem that just illustrates probability theory, whereas on the other hand, it actually gives results that are sophisticated and are actually useful for engineering. So it's sort of on the boundary between theory and practice. And one of the interesting things about it is that the formula for the average waiting time, which is called the Politic formula, which we're going to derive, that formula has in it the variance of the service times. And one of the points for the undergraduates is we have this thing that we define called the variance, which is a measure of variability. And at first, the students just view it as some formula where you plug some stuff in, you get a number, but they don't know what it means. And this is an example that shows what that the variance can be viewed as some kind of fundamental part of the description of a random variable, and that actually affects directly what the answers are when you plug into useful formulas. So here is the theory for the MG1Q. So from the viewpoint of the undergraduate course, I just tell them this. I say if lambda is the arrival rate and x is the service time, then the server utilization is given by, well, we have the symbol rho, and it's given by lambda, which is the arrival rate, times the average service time, E of x, if lambda times E of x is less than 1. And it's given by 1 if lambda times E of x is not less than 1. So that's the definition of the utilization. Now, as you know from your simulation, from everything in the past, that at least if the blocked customers wait in the queue, and if the offered load is less than the number of servers, then, or for one server anyhow, then that corresponds to the actual measured utilization. Okay, the next point statement is that the probability or fraction of customers who have to wait in the queue, probability waiting time is greater than 0, that's equal to rho. So as you know, although it's not clear to the undergraduates, this is sort of surprising because what it says is that what the arriving customers see, this is the fraction of customers who find the server busy, what the arriving customers see and what the outside observer sees turn out to be the same thing if you have Poisson input. Remember, this utilization in the simulation is measured by calculating the fraction of time that the server is busy. And this is calculated by counting how many customers have to wait, dividing by the total number of customers. And because we have Poisson input, Pasta says they're the same thing. So this is sort of interesting. And at least in the case of the utilization, well, it's insensitive to that. Okay, so let's go to the next thing. And this is one of the important results here. This is called the Politic formula. The average value of the waiting time. So in our homeworks, this is the average value of the waiting time when n is equal to infinity. The average value of the waiting time is given by this simple formula. Rho over 1 minus rho, E of x over 2, 1 plus the variance of x divided by the square of the average of x. So this is the famous Politic-Khinchin formula. Politic-Khinchin. K-H-I-N-T-C-H-I-N-E. At least that's the English spelling of it. Politic-Khinchin formula, and it dates from the 1930s. I think Politic published his result in 30 and Khinchin in 32. And historically, this represents not just this formula, but the analysis of MG1, of which this is a part, a consequence. This represents, you might say, the first mathematical investigation of queuing theory for the cases in which you didn't have everything exponential, so you didn't have a birth and death process. So this was the first advance beyond what Erlang did. Then it says, in addition, if the service times are exponentially distributed and the service is FIFO, then the distribution function, let's see, I think I'll write it over here. And you already know this, right? Because, well, you don't know this, but you know this and this from homework 3 if you looked at it for one server. And you know that the distribution function of waiting times is equal to, of course, 0 if t is negative, and 1 minus the Erlang C value, which of course is rho in the case of one server, times e to the minus 1 minus rho, s, which is the number of servers, which in this case is 1, mu t. There's the t, and mu, of course, is the reciprocal of the average service time. Okay, so you know this already, but I'm just stating it for the undergraduate class, and of course there's caveats here. It says if the service times are exponential and if you have FIFO service, and the students tend to forget about that. They don't read the text, they just look at the formula, and they don't realize that it's true, applies in some cases, but it doesn't apply in other cases. So for example, if you ask, in fact, a lot of students in this class did this. If you ask them to calculate rho, then they calculate it always assuming that the offered load is less than the number of servers. And if you plug into that formula for the case in which the offered load is not less than the number of servers, then you get some kind of meaningless result, like a negative number, but a lot of people just write it down anyhow, as if there's no connection between what the theory predicts and what is real. So this is one of the things I try and stress in the class. Okay, and then what I ask them to do is to make these calculations and compare with the results of the simulation. And I have to make the calculations for 3 different cases. And the cases are where the service times are exponential, constant, or uniform. So that means that when they make the calculations, of course, what it turns out to be true is that the utilization and the probability of having to wait in the queue do not depend on the variance or the distribution of the service times, but only depend on the average. However, the average waiting time does not. So when they make the calculations and run the simulation, they see that it doesn't matter as long as the average service time is the same. It doesn't matter whether you have exponential service times, constant service times, or uniform service times. The server is going to always have the same utilization. The fraction of customers who wait on the queue is always going to be the same and is exactly the same as the utilization, but the amount of time they spend waiting on the queue is going to be different because those 3 different cases have different variances. In fact, what we'll see in a moment is that the 2 extreme cases, the exponential and the constant, that means that the average waiting time differs by a factor of 2 or 100%. But nevertheless, the server is busy just as often, and the fraction of customers who wait on the queue is exactly the same. So you have the strange situation, which is supposed to impress people, although, as I say, with the undergraduates, I think a lot of them aren't impressed because they don't even understand what the point is. But what this shows you is that if you are viewing the server, the state of the server, to try and understand what kind of service you're getting, it tells you almost nothing. Because in the numbers that I use here, for example, the utilization turns out to be 80%. So that means that the server is busy 80% of the time, but nevertheless, even though the same fraction of customers find the server busy, In the exponential case, they wait twice as long. So they're just as likely to wait in one case as the other, but the amount of time they wait differs by 100%. So the difference is caused by the variance, and that's one interesting fact. The other interesting fact is that the variance affects the waiting time. It affects how long you wait, but it doesn't affect whether or not you wait. So those are all should be somewhat surprising results. Okay, now, if the service times are exponential, okay, in the case of exponential, if x is exponential, then the variance of x is equal to the mean square. This is something that we prove in class. I think I don't think we proved it in this class, but you could simply make this calculation. This is a fact. In the case in which the x's are constant, then the variance, of course, is 0. So what that means is if I plug into this formula, I find that, well, let me put it here. In the two cases, those two pieces are going to be the same. And what's going to differ is this. Now, if the variance is, if the service times are exponential, then the variance and the mean square are equal, and this multiplying factor is 2. If the service times are constant, then the variance is 0, this ratio is 0, and the multiplying factor is 1. So when you plug into this formula, you see the 2-to-1 ratio. In other words, for the same row, the expected value of the waiting time in the exponential case is equal to twice the expected value of the waiting time in the constant case. This is MM1, that's MD1. So this shows you that these formulas are neat because not only do they give you numerical information, but they give you insight. And insight is really more important, I think, than numerical information. Now, another piece from the viewpoint of the undergraduates is I have to run this simulation, and I'm going to describe this, and then I have to, of course, generate the random variables that correspond to the inter-arrival times and the service times, and that's part of the course, is to show the inverse transform method. And so what this is supposed to illustrate to the students is that if you understand the inverse transform method, and you can write a program, because all the program does is capture the configuration that you're trying to study. So that's just logic and has nothing to do with queuing theory. All it has to do with is being able to translate a particular physical situation, a logical situation, into code. And then the other part has to do with the generation of the random variables that drive it. And then if you know how to generate random variables in the simulation using the inverse transform method, then in effect you can solve any probability problem. And so this is very powerful. All right, so first let me come up with the theory by which I'm going to write this code. Now this code actually generates waiting times in the single server queue. And you already have code for that because you've done that in homework 3. However, in homework 3, I was a little bit more direct. And the way I'm going to do it here, I think, is a little bit more elegant. It's neater, and it has some worthwhile pieces to it. Okay, so here's the theory. And now what I'm trying to do is show how, if you're clever, simulating something that looks as complicated as a queue can really be very easy. And the idea is this. This is called Linley's equation. And it goes sort of like this. You say, well, let's look at this system. And let's say that a customer arrives here at some time t. And when he arrives, he's going to spend a certain length of time waiting. Let's call this t sub n, the arrival time of the nth customer. And then he waits. And the length of time he waits, let's call that wn. It could be 0, because if he arrives and he finds a server idle, he doesn't wait. Then he enters service, and he holds the server for a length of time xn, that's the service time of the nth customer, and then he leaves. Okay, now another customer arrives. There's two possibilities. The next customer might arrive here. Let's say that's t sub n plus 1. Remember now we have FIFO service. So that means that FIFO, first in, first out, service in order of arrival. So if this guy arrives after the guy who arrived in front of him leaves, that means he must find the server idle, and so his waiting time is going to be 0. So this guy's waiting time, w sub n plus 1, is going to be equal to 0. So the interesting case is when the next arrival occurs before the previous arrival has left. Let's say, for the sake of argument, that it happens right here. So this would be t sub n plus 1. So how long does this customer wait? Well, the length of time that he's going to wait is going to be the difference from when he arrives and the customer in front of him leaves. So that's going to be w sub n plus 1. So the waiting time for customer n plus 1 is equal to the waiting time for the previous customer, that's this amount, plus the service time for the previous customer, that's this amount, minus the time that separates their arrivals. And we call that the inter-arrival time. I'll call it IA sub n. So this is sort of a bootstrapping thing. This is a recursive kind of relationship because I can calculate each guy's waiting time in terms of the waiting time and the characteristics of the guy who arrived in front of him. And that's the total logic of my simulation. Now, mathematically, I write it like this with a plus sign because what that means, what the plus sign means is calculate the thing in parentheses. And if it's positive, then take it. And if it's negative, then replace it by 0. If this will be negative if the next arrival occurred after the previous departure. Okay? So this is the big deal right here. I'm going to write a program in which I just express this logic, and everything is there. Okay, so the idea is that I have these urns. And in urn 1, I have the inter-arrival times. In other words, I've got these tickets. And I reach into the urn, I pull out a ticket, and each ticket tells me how much time elapses from one arrival to the next. And then when the arrival is determined, I reach into this urn, and I pull out a ticket, and that represents the service time. And then I put those values into that recursion. I'll write it again. The recursion is that the waiting time for customer n plus 1 is equal to the waiting time for the previous customer plus the service time for the previous customer minus the time between them, minus the inter-arrival time, as long as that's positive. And if it's not, then I set it equal to 0. Okay, so there's the logic of my simulation. Okay, so now let me give you some code. So statement number 100. For I equals 1 to 100,000. So 100,000, based on experience, is enough to have close agreement between simulation and theory, and it all runs very quickly. And I suggest you run it just to see what's going on if you haven't done this in that course. Statement number 110. So now I'm going to find when the next arrival occurs. So I go over to my inter-arrival time urn, and I pick a value out. From the viewpoint of the course, this instruction and the one that samples from this urn, that's the probability part. And the rest of it is simply logic, which in this case is embedded in this simple equation. Okay, so we'll get back to that, but now they have to write the instruction that pulls the ticket out of the inter-arrival time urn. Statement number 120. the current arrival time, t, is equal to the previous arrival time plus the inter-arrival time that I just generated. So this is my clock. Now comes the essential logic of the simulation. The waiting time for the customer whose inter-arrival time I've just generated is equal to the waiting time for the previous customer plus the service time for the previous customer minus the inter-arrival time that I just generated. So the first time through, that's going to be 0 and that's going to be 0. But then after that, they're going to be whatever the previous values were. OK, so you calculate this. That statement, of course, is this. But then I have to check to see whether or not it's negative. So if it's negative, I have to replace it by 0. So statement number 140 says, if the W that I just computed is less than 0, then replace it by 0. Then W equals 0. OK, so the logic for the simulation, that's it. Now I want to calculate some stuff. One of the things I want to calculate is the average waiting time. So I've just calculated a waiting time right here, so I accumulate that. So the sum of the waiting times, SW, is equal to the sum of the waiting times so far plus the waiting time I just calculated. Statement number 170. Now I have to pick my value of x. So now I know that the customer has arrived. OK, here he is right here. And I know how long he's waited. So now I have to pick his service time so that I can calculate the waiting time for the next customer. So now I reach into the service time earn. So that's the other probability piece of this simulation. Then I want to calculate the utilization of the server. Now the utilization is the fraction of time that the server is busy. So what I do is I add up all the service times. That's the total amount of work the server does. Divide that by the total time simulated. The ratio, therefore, is the utilization. So the sum of all the service times is equal to whatever it was before plus the service time I just generated. And then statement number 190, next I. So I run through this loop 100,000 times, and I generate 100,000 inter-arrival times, 100,000 waiting times, 100,000 service times, and then I compute my statistics. So I'm going to print 200. So I'm going to print, first of all, Sx over t. That's the utilization, the sum of all the service times divided by the sum of all the inter-arrival times. Then I want to calculate the fraction of customers who had to wait, probability of waiting time greater than 0. That's C. Now let's see, did I count? Did I miss an? Yes, I missed an instruction here. Statement number 150 says, if the waiting time that I just calculated is greater than 0, that means that that customer was blocked. And so I want to count him. He had to wait in the queue. So then I'll say C is equal to C plus 1. OK, so down here, I calculate C, the total number of customers who had to wait, and I'm going to divide that by 100,000, the total number of customers generated. So this is going to give me the probability of waiting greater than 0. And then I'm going to calculate the average waiting time. That's SW, sum of all the waiting times, divided by 100,000. So this thing right here is rho. That right there is the probability of waiting greater than 0. And this right here is the average waiting time. OK, so what could be simpler? And what could be more elegant? Now, I have to put the stuff in here that's going to correspond to the inter-arrival times and the service times. If we have Poisson input, and I try and explain to the class what that means, and we derived that earlier in the course, that means that the inter-arrival times are exponential. And it says here that assume that the inter-arrival times are exponentially distributed with a mean value of 0.625. So the reciprocal is 1.6. That corresponds to a rate of 1.6. Okay, so that means that IA would be equal to minus 0.625 times the log of 1 minus a random number. And this instruction would be the same instruction for every case. What I'm going to vary here is I'm going to vary the service times. So I have statement number 170. I have 3 different service times. The first case is the service times are exponential with an average of 1/2. So x is equal to minus 0.5 times the log of 1 minus a random number. In the second case, the service times are constant with a value of 0.5. So x is equal to 0.5. In the third case, the service times are supposed to be uniform. If they're uniform between 0 and 1, then their average will be 1/2. And to generate a uniform random variable between 0 and 1, I just use the random number generator directly. So I write x equals RND. So the student has to run the program 3 times, once with exponential service times, once with constant service times, once with uniform service times, and then calculate the stuff that's in the table. Now, if you run this program, the results that you get here should be the same as if you ran your homework number 4, except for one server. Homework 4, let me get the numbers right. Homework 4 is the Erlang delay model, right? Okay, so in other words, you have a choice. The code here is, of course, much different. And what I like about this, what's so elegant about it, is that all the logic is right here in this recursive relationship. And one of the important things about probability is that a lot of difficult problems are solved by representing the probabilities in terms of each other. That is some kind of functional relationship rather than getting explicit formulas for things. And this requires the students then to actually calculate the mean, calculate the variance, plug things in, run this. So at the end of the course, everything comes together, or is supposed to anyhow, with this one problem. Okay, so let me write down what's in the table.
I have a quick question.
Yes?
How would you calculate on the mean waiting time if server utilization was 1?
You mean in theory or?
Yeah, theory.
Well, if the server utilization is 1, in theory, if there's an infinite number of, let's start again. Question is, how do you calculate the mean waiting time if the utilization is 1? The only time the utilization could be 100% if you have random input is when you have an infinite number of waiting positions. Okay, in that case, if the offered load is equal to or greater than the number of servers, then you will have an infinite queue, so the utilization in principle will be 1. So in fact, in homework number 4, I asked people to calculate the utilization for the case in which the offered load was greater than the number of servers. And in theory, it should be 1 in every case. And when you ran the simulation, you should see that the simulation should give you values very close to 1. So in this case, the theoretical answer is, if you have an infinite number of servers and your offered load is larger than or equal to the number of servers, then the utilization will be 100%. Now, if you have a finite number of servers, then the utilization will be less than 100% because not everybody who arrives will get served. It might be very close to 100%. In other words, what you should see when you do your homework is that as the n gets bigger, the utilization approaches 100%. But it'll never be 100%, at least in theory, unless you have an infinite number of waiting positions. Is there a question there?
You said if n was a finite number, if it was finite number of servers or finite number of waiting positions?
If I said servers, it was a mistake. I meant waiting positions. Well, wait, depends on what the question was. Okay. If the offered load is greater than or equal to the number of servers, and if the number of waiting positions is infinite, then the utilization is 100%. Utilization is 1. It's also true that the average waiting time will be infinity. And that'll be true regardless of whether I have Poisson input, exponential service times, or anything. Those results are insensitive to these distributions, and in fact are consequences of Little's theorem. If I have a finite number of waiting positions, then not everybody who arrives will get served, even if the offered load is greater than the number of servers. So therefore, the actual utilization will be less than 100%, and you have to calculate that. And so that's one of the things you're going to see when you do the homework. Now, in your homework, what I'm asking you to do is to look at the case where the number of waiting positions is finite. So you have to take the code either for homework 4 or for this. You could use this code because it doesn't really make any difference. This is actually more elegant. In any case, what you have to do is you have to do something that describes the states of the waiting positions and determines whether or not all waiting positions are busy. So whether you use this code or whether you use the code that you already used for homework 4 but setting the number of servers equal to 1, you still have to make the same change to go from infinite number of waiting positions to finite number of waiting positions. So this one is actually simpler because the code is shorter and more transparent. But it doesn't really make any difference. Okay, so my suggestion is that you run this code and convince yourself that the Politic-Kinchin formula is correct, and because later, homework 7, now we're going to start looking at the case where we actually have to worry about the case of non-exponential service times. Well, that's in homework 6, I should say. Okay, so let me repeat what I just said there. For homework 5, it doesn't matter, and in fact for homework 6, it doesn't matter whether you use the simulation here and upgrade this, or the simulation you've already done and upgrade that, because the upgrade is the same in both cases. But the theory is different. Okay, the theory you know how to do for homework 5, you don't know how to do for homework 6, except for the boundary cases. The boundary cases are Erlang B and Erlang C. For Erlang B, you know that the results are insensitive to service times. So therefore, homework 5 and homework 6 are going to have the same answers for the case where n is equal to 0. And in the case in which n is equal to infinity, you have a formula, but the answers are going to be different because, in fact, you know that the average waiting time for the case of constant service times is going to be half as much as for the average waiting time for exponential service times. Of course, the simulations will show that clearly. Okay, so in this problem then, so here's what I asked the students to do. Okay, so I gave them the 3 cases. So there's case 1, exponential, case 2, constant, case 3, uniform. And they're supposed to calculate utilization. That's what we call rho. Of course, there's theory and there's simulation. And then you have to calculate the probability of waiting greater than 0. Theory, simulation. Then I asked them to calculate the probability of waiting greater than 1. And that I didn't give them the code for. And of course, the students have a lot of problem with that because they really don't understand what's happening here. So you have to tell them, well, what does it mean to say probability greater than 1? You simply count how many of the W's are greater than 1, and then divide that by the total number of customers, and that's the probability of W greater than 1. One of the questions that they're asked to do here is to calculate the distribution function. Now, the distribution function, by definition, is the probability that W is less than or equal to T. And in the calculation here, I asked them to do this because I have a formula for this for the case of exponential service times. But in any other case, you don't have a formula. That's one of the things I'm trying to impress on them and you. Now, when you calculate this, I asked them to do it for various values of t, and they have to upgrade the simulation. Means I have to take this simulation and I have to ask for each customer they want to count how many of those waiting times are less than 0, less than or equal to 1, less than or equal to 2, and so forth, and then divide each of those by 100,000, and that'll give you the fraction less than that. So one of the ones that they have to calculate as they go along is the distribution function of W evaluated at 0.5. Evaluated at 1, excuse me. So it always surprises me, this is something you have to recognize when you teach this kind of thing, is that the students have a program and they have a theory that calculates this, but nevertheless they can't calculate that because they don't know that that is 1 minus this, even though, of course, that's the way this thing was derived. You have to point it out to them, and at the end, a lot of them still don't get it. They end in the homework and they have that part blank because they have no idea what they're doing. So this is just maybe a lecture on how some of the stuff, when you teach it and it's obvious and you're trying to illustrate some interesting fine points, it turns out that most of the students have no idea what you're talking about because the stuff that you gloss over because it's too simple to even mention, that's where they get lost. And so if they can't do that, they have no idea what the rest of it's about. Well, anyhow, that's the reason that this is in here. Okay, and then when you have to calculate this, I'm trying to impress on them that in the simulation, the answers do not depend on what the distribution of the inter-arrival times and service times are. But in the theory, it does. And if I have exponential service times, I can calculate this. But if I have constant service times or anything other than exponential, I can't calculate it. So I write NA for not applicable. So I'm trying to impress on the students that here's a case in which I have a simulation. The simulation can answer any question, but it only gives me data. It doesn't give me any insight. The theory, when it works, gives me insight because it gives me nice, simple formulas, but it only works in certain cases. And the way the problem is stated, it says, if the service times are exponential and if you have FIFO service, then such and such a formula applies. Most of the students don't understand, though, why this is NA and this is a formula, because they don't read the statement that says if it's true, then it applies. If it's not true, well, it may not apply. And the simulation shows that it doesn't apply because the answers come out to be different for different service time distributions. So from your point of view, this should all be simple and make a lot of sense. And I think it's worth looking at, especially since this Linley's result is very nice. And so this is sort of an introduction to the MG1Q. Now the question is, how do I calculate, how do I get the theory for the things that are not insensitive to service times? In particular, how do I derive the formula for the average waiting time, the famous Politic-Kinchin formula, which has the variance of the service times in the formula. So this formula works for any distribution of service times. All you have to do is know how to calculate the variance. From the undergraduate point of view, I give them the formula and the exercise to calculate the variance. From your point of view, where does this formula come from? It comes from the theory of MG1. We can't analyze MG1 by using rate up equals rate down for the reasons that I stated earlier, and so we have to develop some new tools, and so that's where we are now. Okay, so before I go on, we don't have that much time anyhow. Are there any questions about the big picture here? So what I have to do now is I have to develop the theory so that you can analyze MG1. Now, what you might characterize the course this way. You might say that what we've done so far is elementary queuing theory. Okay, it's elementary. It's tricky stuff, especially the stuff about POSTA, for example, and queuing networks and Burke's theorem and feedback and all that kind of stuff. It's very tricky, but it's elementary in the sense that there's not much mathematics involved. There may be some algebra, but there's no advanced mathematics. So now we're going to go into what's called maybe intermediate queuing theory. So now I'm going to use some new things like Laplace-Stieltjes transforms and generating functions and Riemann-Stieltjes integration. So these are steps up in terms of the theoretical mathematics necessary to do this, but it's not hard. It's just something that you don't know yet. So I'll cover that, and then we'll apply that to this stuff here so we can do the MG1. The MG1 is called the embedded Markov chain. That's the method we're going to use. So let me briefly state what I'm going to do here. And then next time I'll start developing the theory so we can do this. And this theory is really neat, and it's not hard. It's just something that's more advanced and is usually taught in an undergraduate program. Okay, so what happens here is we have these customers arriving, and arrivals produce service times, and so you have sequences of service times like that. And then eventually you have the last service time, and then the process starts over again with the next arrival to an idle server, like that. Now, what we've done up to this point is we have said, let's take the viewpoint of an arbitrary arrival. So there's an arbitrary arrival. Every arrival either finds a server idle or not. And if he doesn't find it idle, he arrives during a service time. So what we did is we said, okay, we have an arbitrary arrival, and all we'll do is relate the probabilities to the number of customers present when the arrival occurs. We could do that because of pasta and because with the exponential assumption about the underlying distributions, there was no memory. But now the service times are not exponential anymore. We're still going to keep the arrival process Poisson. If we get rid of that, we're in deep doo-doo. So we'll keep the arrival process Poisson, but now the service times are not exponential. That means that if I take the viewpoint of the outside observer or the arriving customer, whatever, I'm going to be looking at the system at a time which in general is in the middle of a service time. And that means that I have introduced memory. So how am I going to get away with that? And the answer is, well, what I'm going to do is I'm going to look at the system not at arbitrary times or not at arrival times. I'm going to look at it at departure times. So, for example, there's a departure. There's a departure. So I'm going to write equations not for the probability that the system is in state J, call that Pj, or the probability that an arrival finds a system in state J, call that pi j, but the probability that a departure leaves the system in state J. So the star here represents the probability from the viewpoint of a departing customer. Now, that's easier to do because I know that when a customer departs, I know how much time there is between successive customers. It's a service time. So this length of time, I know its distribution function. So all I need to know in order to get equations for the pi stars is I need to know how much time separates the departures and how many arrivals occur during a service time. But if they occur according to a Poisson process, and I know the distribution of that time, and the point here, the beauty of it is, if I'm embedding, this is said, you're said to embed a Markov chain. Okay, embed means that you pick points out of the continuum, and it's a Markov chain for technical reasons. That's what it's called. But we don't have to know the theory of Markov chains in detail in order to be able to solve this problem, because this is a very special context. Now, what this says is that by this embedding process, that means that the instance I look at the thing are separated by times whose distribution I know, because I know that I'm always starting and ending at the beginning. That is, this is a full service time. It's not an interrupted service time. And since I have a Poisson process, it's easy to calculate the distribution of the number that arrived during a service time. And that gives me information about the probabilities, the probability that an arbitrary departure, the number left behind is j. But I don't want the number left behind. I want the number that the arriving customer finds, not what he leaves behind. But it turns out that there's a theorem, also due to Burke, by the way. This is an interesting point. I'll get to this later. That says that these things are equal as long as this is what's called a one-step process. That is, you go up and down one state at a time, which is true in this case. So in equilibrium, the departing customer's viewpoint is the same as the arriving customer's viewpoint. And because we have Poisson input by pasta, it's the same as the outside observer's viewpoint. So what I do is I write equations from this point of view, and I interpret, depending on what my where I am, from this point of view or this point of view. In other words, I go back and forth in the interpretation of the results because I have these neat theorems. I have this theorem here and this theorem here. This is pasta. This is the one-step theorem, and everything is equal. So what I need to do is I need to describe the method by which I calculate these guys. And then based on this, I'm going to be able to calculate the distribution of waiting times. And that's really neat because what's going to happen is this. I'm going to say that an arrival occurs, he waits, and then he leaves. Now, if I know how many customers he leaves behind him, then I know how many arrived during his waiting time. Because if service is FIFO, I leave behind me, when I leave, exactly those customers who arrived while I was waiting and being served. In other words, it takes me a certain length of time to flow through the system. That length of time is actually my waiting time plus my service time. Okay, now, when I leave, the customers that are there when I leave are the customers who arrived between when I arrived and between when I left, if I have FIFO service. If I know how many arrived, then I know how long this interval is. Actually, I don't know how many arrived. What I will know is the distribution of the number I left behind. But the distribution of the number I left behind is a distribution of the number that arrived during my sojourn time. And if I know that distribution, and I know that they arrived according to a Poisson process, that's our assumption here, then I know something about how much time, what the time interval was during which they arrived. That is, I have an interval, and I have a number that arrived during that interval. Obviously, the bigger the interval is, the more customers are going to arrive. The more customers who arrive, the bigger the interval is. So if I know something about how long the interval is, I could say something about how many arrived. If I say something about how many arrived, I could say something about how long the interval is. It turns out if they arrived according to a Poisson process, then there's a very simple relationship between the number that arrived and the length of the period during which they arrived. And that relationship is expressed in terms of the so-called generating function of the number of arrivals, which is a discrete distribution, and the Laplace-Dieltjes transform of the length of time. That length of time is a continuous distribution. And so we're going to go back and forth between the discrete values, which represent the numbers of customers arriving, and the continuous values, which represent how much time they spend. And that's analogous to Little's theorem in